Okay, all right. So let us begin today's session. This is session number 15. So till now we have covered the modeling of transmission line, and then before that we have seen that in how to find the inductance and capacitance of transmission lines, and then after modeling of transmission line we have seen the power flow equations in transmission line. So we have seen the power flow equations in transmission line based on the voltage given at the busage and the line parameters. We can find the uh, sending end and receiving end active and reactive power available at the busage. So now today we are going to see the reactive power compensation techniques. I think some part of this reactive power compensation and power factor correction has been covered in the previous session, that is session number 8. And today we are going to see more detail about this reactive power compensation, and we will solve problems uh, from the gate. So coming to this reactive power compensation, so what is reactive power compensation? So the first question comes is that what is reactive power compensation? So it is technique by which we can change the reactive power flow in the line or the reactive power demand at the busage. So either we can do it by two means. The first is series compensation and second one is shunt compensation. In series compensation, we are adding this series inductor or capacitors in the series with the transmission or distribution lines, and in the shunt compensation we are we are adding shunt reactors and compensation at the busage, at the load busage. So what are this purpose for series and shunt compensation? So series compensation is mainly used to increase the power transfer capability of line and limit the current flow. So this series compensation is mainly used to increase the maximum power transfer capability of line and limit the current flow. So the maximum this series capacitor increase this maximum power transfer capability of line, and the series reactor limit the current flow in the line. So we know this equation, V is equal to P max, maximum power transfer in the line. P max is magnitude of voltage at the busage at the end of line, and it is divided by this reactance of line for a lossless short transmission line. So if we are going to change this reactance of line, then if we are having this mostly this inductive in nature, so we are going to add series capacitor to the line so that we can reduce this reactance such that this maximum power transfer capability of line increases. Now the second one is the shunt compensation, that is mainly used to improve the power factor and the voltage profile. So we will see this part more in detail, and by applying both series and shunt compensation to transmission lines, we can transmit large amounts of power efficiently and within desired voltage constants. Mostly utilities use this shunt compensation, and this is more we can see in our uh, power system. Now come to this theoretical questions that have been asked in GATE. So the first question is that shunt reactors are sometimes used in high voltage transmission system, and the options are limit the short circuit current through the line, compensate for the series reactance of the line under heavily loaded condition, limit over voltages at the load side under lightly loaded condition, and D option is compensate for the voltage drop in the line under heavily loaded condition. So this is asked for shunt reactors. So if we see the compensation about individually, like shunt capacitor, the main purpose of shunt capacitor is to improve the power factor, and the shunt reactor is to reduce the Ferranti effect. And we know that in Ferranti effect, if we are having lightly loaded condition, under lightly loaded condition, this magnitude at the receiving end of the line goes down, goes down in comparison to the sending end voltage. So that is called Ferranti effect. And to reduce the Ferranti effects, to want to maintain the voltage at the receiving end of line, we use the shunt reactor. And the series reactor is to increase the maximum power transfer capability of line, and the series reactor is to limit the fault current and reduce the current ripples. So now coming to these options, the first option is that limit the short circuit current through the line. So this is done by the series reactor, not by shunt reactor. So this work is done by the series reactor. So this option is going to be incorrect. And the second option is that compensate for the series reactance of the line under heavily loaded condition. So this is done by the series capacitor. And third option is that limit over voltages at the load side under lightly loaded condition. So this is Ferranti effect, and so this is done by this shunt reactor. So C option is going to be correct. And if you want to see the last option, the option is that compensate for the voltage drop in the line under heavily loaded condition. And this is also done by this series capacitor. Voltage drop means like we are reducing the X in of the line. How can we can do that? By adding this series capacitor. So it will come XL minus XC. And B option is just similar. Sorry. So so this is the first problem, and this problem has been asked in GATE 2014, and it is set to, it is of 1 mark. If you face any doubt or any problem, you can ask me anytime. Now coming to the second problem. Yes, Anil.
Sir, please explain shunt capacitor in a circuit so that it is very it will clear more for me.
Shunt capacitor I will
How
describe in detail, but for shunt reactor, like shunt reactor, how, okay, uh, shunt reactor, okay. Shunt reactor, you can like see Ferranti effect. I think you are familiar with this word Ferranti effect, right? Hello?
sir, in Franti effect, the output voltage is become higher than voltage applied at a supply side.
In Ferranti effect, if the load is very low, means in
Receiving voltage is greater than
yeah,
supply voltage.
yeah, correct. Suppose if the whatever the rated load we are having, but the load is very light in that condition, what happens is that voltage at the receiving end becomes greater than the sending end. So what we will do? So in that condition, we add shunt reactor.
Shunt reactor.
So like this is load bus and PL. I have write it lightly load. Means whatever the rated load in comparison to that it is very low value. So in that condition B add reactor. So what reactor does, as this reactor brings reactors demand more reactive power from the generator side, from the line. So if reactive power reactive power demand increases, like this increases through the line, so this voltage at the receiving end comes down. So that's why we use this shunt reactor for to reduce the effect of Ferranti effect. So
Sir, is there is any direct relation between voltage and reactive power?
yeah, this is like if you want to calculate this Excel, how you can calculate QL is equal to
We
if you are
we
taking phase value, suppose you are taking line to line value. So it is simply that
we
VRLN
square by v square by x.
Excel. So just let think in this way. If this voltage at the receiving end getting down, in that case you have to do the shunt capacitive compensation. And if the voltage at the receiving end is going higher, in that case you have to do the shunt shunt reactor compensation, not capacitor. You have to add this reactor at the receiving end. And if this voltage at the receiving end going down, then you have to do the shunt capacitor, add the shunt capacitor here at the bus. Okay.
Okay, sir.
So now coming to the next problem. So the next problem is that for enhancing the power transmission in a long EHV transmission line, the most preferred method is to connect a.
Option C, sir.
Yes,
Option C.
yeah, correct. Option C is correct. So in this problem, it is asked about that we have to enhance the power transmission. So how we can do? We use this series capacitor, like
P
yeah,
equal EV by X sine delta.
X. We have seen here we have seen in here this X we have to reduce, so we will do this series capacitive compensation, so that we can increase the power transfer capability of line. And we can see other options also, so that your concept will be more clear. First option, that series inductive compensator in line, this will be incorrect. See what series inductive compensator will do, it will limit the fault current or reduce the current ripples. And the second option, the shunt inductive compensator. We have seen that it is used to reduce the effect of Ferranti effect. And D option is that shunt capacitive compensator. We use this for the improve the power factor or maintain the voltage profile at the load bus. So this is asked in, I think it is also gate problem, and this is asked in, this is asked in gate 2011. It is of 1 mark. Now third problem is that it is also,
Sir, in question two, sir, show me question two. Capacitor, how it will increase the maximum power transfer capability of line?
yeah. So we know this for a lossless or transmission line. We know this expression sine delta. So if we want to write the maximum value of can that can flow through the transmission line, what will be that? V1 V2 divided by reactance of the line. So if we want to increase this maximum power transfer capability of line, so this should be reduced reactance of line, and we know that X is equal to XL minus XC. So if we add this series capacitor value to the line, then this will get down. So in that way you can understand. You have to do the series capacitor compensation to enhance the power transfer capability of line. You got it or not?
Okay, sir. Got it, sir.
Yeah, it is very simple. Just revise one or two times more. You just write yourself after completing this session. You just write yourself that what this shunt and series capacitor and reactor what they do and how this is going to be done based on this mathematical expression. And third problem is that you have to match this what are the purposes of this. So list one is that use of the this compensation, and the list two is the compensator
Improve the
characteristics.
improve the power factor means shunt capacitor, sir. Two,
Yeah, so improve the power factor, that is shunt capacitor.
and
Uh,
reducing the current ripples means series reactor.
yeah,
Reactor.
yeah,
Increasing the power flow in the line means series capacitor.
improving the power flow in series capacitor. Correct.
Reducing the Ferranti effect means shunt reactor.
So based on the option,
Option
A is for A,
option
A is 2 and B is 4. So only B option is matching, and C is 3 and D is 1. And this is asked in
Sir,
yes.
sir, reduce the current repel is option for series reactor, sir. How, sir? Explain, sir.
Reduce the current ripple. What is the inductive property? Inductor does not.
opposes the sudden change in current.
Yeah, from there it came. From there this principle came. In during fault, what happens? There is a suddenly large amount of current flow through the line. So it opposes that change in current. So such that our circuit breaker or our other equipment such that our circuit breaker gets stripped and other equipment will not get damaged. So that's why we use this series reactor to reduce the current ripples, so that we can save our equipments during faults.
Okay, sir.
So it is of asked in GATE 2019, it is of 2 marks. So the purpose of series reactor are I have shown here. So series reactor does two things. It is limiting the fault current also and reducing the current ripple also. The more the series reactor value, the ripple will be less. Now we will see the shunt reactive power compensation. And the key idea of reactive compensation is to supply. We have seen, I think, these slides before. So I will just go revise it through quickly and we will solve the problems based on that. So the key idea of reactive compensation is to supply reactive power locally. We are not doing the reactive shunt reactive compensation at the sending end. We are doing at the receiving end. Wherever the demand of reactive power is there, we will do at that end only. So this results in reduction of line losses, which are equal to IR square decrease, and that also leads to supply more load over the same wire, and that leads to lower current, allows utility to a small wires, and this also leads to improvement of bus voltage profile, and thus voltage drop on the line is less, and this leads to also power factor correction. This is also called volt var control. So we are having distribution substation, and these are the nodes where this load demand is having both active and reactive power in nature. So what we do this reactive power source like such that we can fulfill their demand at the local in, not at the sending in. So there are different ways of doing shunt reactive power compensation. Like first one is a static compensator that you do by inductor or capacitor, whatever the nature of reactive power demand. Based on that, we can use this shunt inductor or capacitor. Mostly the reactive power demand is of inductive in nature, so we will do the compensating by the use of the capacitor. So this shunt compensator can supply both leading and lagging wires, and it is of cheaper in cost, and this overloading for short duration is not possible. This is very important for a static compensator. Overloading is not possible. If you do overloading, your may inductor or capacitor may blast or may burnt. So this will very important. And another disadvantage of this static compensator is that during voltage dip, it supplies reduced wires. So as the voltage drop at the load end, it will supply, irrespective of it should supply more reactive power, it will supply less reactive power. So this is also disadvantage. It is came from this Q is equal to VL square divided by X. So if this voltage drop down, this reactive power will also get dropped down. So this is the disadvantage of a static compensator. And if we see the rotating compensator that we do by synchronous condenser, it can supply leading and lagging 50% battery capacity. Sorry, here what's it? 50 or can supply leading and lagging watts, and this is also, and this rotating compensator is a fast and continuous control and can be overloaded for short duration. So this is the difference between a static compensation and rotating compensation. It can be overloaded for short duration, but a static compensator will get burnt if you do overloading, and it can arrest the voltage dip. If there is a voltage dip, it may restore to the, it can restore to the original voltage value. So it can maintain the voltage profile, and it introduces the inertia and therefore improves the stability of system. Since this is a rotating machine, synchronous condenser, so it introduces the inertia and therefore improves the stability of system. And it is expensive and uneconomical for a small size synchronous condenser. So if, generally for a smaller size, we prefer this static compensator, and for larger size, we prefer synchronous condenser. And third one is the custom power devices, and this includes DS-STATCOM. Distribution static compensator. It is also called as series active power filter. It is also called as series active power filter. And Other examples are like DVR, sorry, it is parallel active power. The STATCOM connects parallel to the line, and other example is that DVR, dynamic voltage restorer. So this is also called as series active power filter. And other examples are UPQC, Unified Power Quality Conditioner. So this UPQC is combination of both DSTATCOM and DVR. So it will both compensate the voltage voltage profile or also compensate for the active reactive power demand, and it also does the compensation for nonlinear load also. So these are for higher, these are not for undergrad course, custom power devices and distributed generation units. These are for higher courses. So in undergrad course, basically these two are important: a static compensator and rotating compensator. Now we mainly focus on the shunt capacitor compensation because this is generally the more practical case and generally more questions asked from this side only. So shunt capacitor for power factor correction. First we will see this power triangle. So there is substation and it is connected to through this line, and load is connected at this node. So the having demand of active power P1 and reactive power Q1. So this will comes from the substation through the line. And if you want to make the power triangle for the load, this is active power P1, and then we are having this uh, orthogonal to active power Q1, and this vector sum of active and active power will give you apparent power, and theta 1 is the power factor angle, and cos theta 1 is the power factor, and cos theta 1, how you can write P1 divided by S1. So this will give you power factor. Till here any doubt, Anil and Biray and Nagula?
No doubt, sir. No doubt.
So what is your I don't know how to pronounce your name. So what your friend used to call you? Biray or
Veeraya. Veeraya.
Biraya? Okay,
Nagulla is my surname, sir.
okay, okay. Biraya. Thanks. So now when we do the shunt capacitor compensation, then the case will be like this. So it is of QC rating, and it is installed at the node where the load is connected, and this power factor can be improved from cos theta 1 to cos theta 2. So we can see that this earlier this reactive power demand of the load is fulfilled through this all fulfilled through this source side, not at the local end. And if by installing the shunt capacitor at the load end, so we can provide this reactive power locally, such that this reactive power demand through the line decreases, and overall this power factor will get increased. So here I have shown, you can write this QC value is just opposite to the, because this is inductive reactive power is inductive nature, and QC the capacitive reactive power, so this opposite in nature, and by subtracting QC from Q1 you will get Q2. So finally you will get this power factor cos theta 2 like this, and this is having more value because this cost and this theta to power factor angle get reduced, so that cos theta to value will get decreased.
Sir,
Yes.
sir, if you connect series inductor, then the same thing will happen, just like
No, no.
connected shunt capacitor.
In that case, if you are adding, if you are, if your reactive power demand at the load in reactive power demand of load is inductive in nature, and you are adding series reactor, in that case it will worsen your power factor. It will add the reactive power here. So like if you are having
Sir, inductor consume reactive power, sir.
shunt reactor, I will show you what this consume or supplies. If you are having shunt reactor, so irrespective of reducing your, like this is P1 and Q1, and this, suppose this P1 plus JQ1, and suppose if this inductor is supplying QL reactive power, so it will not reduce this reactive power, reactive power of total reactive power, so it will get as to this one. So overall your power factor angle will get increased, and this earlier power factor angle is theta 1, so now this become theta 2, so this will worsen your power factor. So power factor cos theta 2 will get down.
Decrease. Decrease.
So this worsen your power factor. So this is that is the case. So for improving the power factor, we do the shunt capacitor compensation, not this shunt reactor compensation.
Sir,
Yes.
if you add a in series inductor, then power factor will increase. Series inductor.
Series inductor, if you see the power factor at this total power factor at the load in, then nothing will impact because, but if you see the power factor of the, if you see the power factor of the like generator side, then it will get also worsen. So you have to compromise with the things, like you cannot add more inductance to the value so that the power factor become broken from the, for the generator side also. You have to do such that whatever we do the series we do the series reactor compensation to increase the power flow contributed line, so that the main purpose is that it does not lead to uh, deteriorate your power factor more. So we have to see we have to do like trade-off, not any means like you cannot go beyond that. Correct. And the don't confuse don't merge things with each other. So series reactor, that means you are reducing the reactance of line. Sorry, series reactor means that you are improving the, so series, what you are, a series reactor or series capacitor?
Series reactor.
Okay, sorry. So series, main purpose series reactor is to limit the power, uh, limit the current or limit the fault current. So in that case, of course, this series reactor will also demand the reactive power from the generator side. So it will worsen the power factor for the generator, but it also leads to improve the reduce the current ripple and limit the fault current. Right? You got it or not? I should repeat again.
Sir, got it, sir.
So the what is the main purpose you are using for the compensator? Just remember that thing. I will show you what is the purpose of what this inductor and capacitor supplies lagging or leading reactive power. I will show you in the next slides.
Okay, sir.
So here is one of the example for this power factor correction example. So here we are having a load with power factor 0.8 lagging, and you would like to correct the power factor to 0.95 lagging. What would be the capacitor size? So we know that required power factor is 0.95. So the power factor required power factor angle is 18.2 degree, 2 degree. So just we have to uh, apply this trigonometry formula so that we can find this required capacitor size value. So we will get this required capacitor size value with 33.7 kVAr. And we have seen the effect of reactive power on power factor. Suppose if you are having load 100 kVA and power factor is 1, then here if your power factor is 1, then P is equal to S. Whatever the total load, that all are active power. And suppose if your if your power factor get down, and if you are having P is equal to 100 kilowatt, then this reactive power demand increases. So we can any other case, if power factor again goes down, then this reactive power goes up, like from 48.43 kVAr it goes to 75 kVAr. And again if we see this power factor is 0.70, then again it goes above from 75 kVAr to 102 kVAr. And for the last case, if power factor goes again down,
Sir, your screen not visible, sir.
Sir,
Screen not
visible for
visible,
me,
sir.
sir. Sir, screen is visible for me, sir.
okay, I think the network issue.
Okay, I will rejoin, sir.
Yeah, yeah, sure, Virey. So Anil, here you can see that what is the effect of this rushing the power factor. Means this reactive
Yes,
power
sir.
demand
Sir,
from the
power
generator increases.
factor,
Yes,
sir, power factor is reducing and reactive power demand is increasing.
yes,
Okay, sir.
yeah. So reactive power demand from the generator side it increasing. So that's why we called it this power factor is getting down. Now we will see another case. Here we are maintaining this apparent power equal. In previous case, we are assuming this active power. We are assuming the active power remains constant throughout in all case. In this case, we are assuming the apparent power remain constant. So if you are assuming this apparent power remain constant, then if power factor goes down, then this leads to lesser amount of active power and more amount of reactive power, and reactive power get increased as this power factor reducing down. So these are the illustrative examples. From there we can understand the effect of reactive power on power factor. Now this concept of leading and lagging reactive power factors. So the concept of lagging and leading power factors depends on the direction of flow of reactive power, and this sign convention is positive for load if consuming real or reactive power. So power factor is lagging means this load consumes reactive power, and if we are saying this only reactive power, then we have to assume that we are talking about the lagging reactive power. So if load is consuming lagging reactive power, that means it is supplying leading reactive power. And just vice versa, if power factor is leading, that means Q is negative and load supplies reactive power. And if we are writing down nothing lagging or leading, then you have to assume the lagging reactive power. That means load supply lagging reactive power, and if you write down in terms of consumption, then you have to write that load consumes leading reactive power. So this is the thing. So inductive load consumes lagging reactive power, and capacitive load supply lagging reactive power. So these things be used in the solving the problems for power factor correction. Anil, you got it here or not? Anil?
Yes, sir. Sir, these things have to
Yes.
you have to mug up.
Just you have to write, keep in mind the convention. Like if load is consuming reactive power, that means it is in it is of positive in nature, and if it is negative, that means it is supplying reactive power. And capacitor supplies reactive
Oh,
power, and inductors consumes reactive power.
okay, sir. Okay, sir.
Yes. So now we will solve some gate problems. I think here I have noted down or not. Yes. So this problem, yes. So this problem is little bit older. Gate 2003. It is of 2 marks. So this question is that a valence delta connected load of 8 plus J6 ohm per phase is connected to a 400 volt 50 hertz three phase supply lines. If the input power factor is to be improved to 2.9 by connecting a bank of star connected capacitor, the required kVAR of the bank is. So here suppose this line voltage is given, so we can assume that let voltage phase voltage is 400 divided by root 3 at the angle of 0 volt, and this delta connected load is given, so we can convert into a star. So Z star is equal to Z load divided by 3, so 8 plus J6 divided by 3, so it will give you 2.667 plus J2. Therefore you can find IA is equal to VA divided by Z star. So from here 400 divided by root 3, 2.667 plus J2, so it will give you 40 root 3 minus 36.87 ampere. So power factor before the compensation is cos phi 1, cos 36.87, negative that denotes that it is lagging nature, so it will come as 0.8 lagging. So we have converted load into a star like this one. You can do the calculation in delta also based on your convenience. A C B. So the required power factor is like it is improved. So improved improved power factor means power, we assume it as power factor 2. So it is given as cos phi 2 is given as 0.9 lagging. So from here we can find phi 2. Phi 2 will come as 25.842 degree. Now, now we can calculate the active. So we can calculate the active and reactive power demand of load. So like we are writing PL as active power demand of load. So 3 into 3 into VA IA cos phi 1. You can write here load demand. So you put all these values. 3 into 400 divided by root 3. IA is 40 root 3. Cos phi is 0.8. So you will get this amount as 38400 watt, and QL is 3 into VA into IA sin phi 1. So you will get this one, 3 into 400 divided by root 3 into 40 root 3. If cos phi is 0.8, then sin phi is 0.6, then it is 28800 bar. So we have found out this active and active power demand of load. Now we will make the power factor triangle. So PL is nothing to active power demand is nothing to do with the compensation. And suppose this is my QL.
10.2, sir.
How much?
10.2.
Yeah, correct,
10.2.
correct. So this one is, we have assumed this phi 1 before compensation, and this is after compensation phi 2, and this reactive power will get reduced, QL minus QC. This is QC. So just we will apply this trigonometry expression. Tan phi 2 is QL minus QC divided by PL. So tan phi 2 is how much? Phi 2 is, we have 25.842. QL we have calculated. QL is coming as 28,800 minus QC, and PL is 38,400 watt. So do simplification. So it will be 18598 is equal to 28800 minus QC. So QC will be 10202 var. So it equivalent to 10.2 kVAR. So I have this is correct answer is B. So now I have one question here. So can this, if this in this problem it is asked that what will the size of delta connected capacitor, what would be the answer?
Sir, capacitance, value of capacitance. C, C.
Bank size
Banks.
means like reactive power value. Not capacitance value. I am asking about the reactive power bank size.
Sir, 32.4, sir.
No. So
No, no.
it is
Historical data.
don't get confused. I am telling the answer. I we have less time. So whenever it is asking about the bank size, you have to nothing related with us whether it is connected star or delta. When it is asked about this like capacitance value, then you have to bother about this whether it is connected star or delta, because because you calculate q value either from a star or either from delta, it will remain same, because you have to add that add that rating rating value should be add to the, parallel to the load, but it is asked about this c size, then it gets 10, it gets it gets changed for delta gets changed for delta or star value depending upon the connection. So there is nothing to do with this total value, this q value, either it is in a star or delta. It is just like that a load is connected in a star or delta having rating is given, having a specific rating is given. So if you are connected in a star, then this impedance value will get changed that of delta value. But this total power demand for that load, it is remain as it is. Either you connect in load a star, either you connect in delta. So this is if you solve this problem in delta, then you will get the same answer. Okay, you got it, Viray.
Sir, yes, sir, got it, sir. Thank you, sir.
Mhm. Now, next problem. So a 400 volt 50 or 3 phase balance source supplies a star connected load whose rating is 12 root 3 kVA, 0.8 power factor lag. The rating of the delta connected reactive power bank necessary to bring up the power factor to unity is. So this is problem is from GATE 2006. It is of 2 marks and it is very easy question. So everything is given here. First we will find the load demand. So load demand is PL is equal to S into cos phi. If you got answer, just tell or type in the chat box. 12 root 3 into 0.8, so it will be 16.63 kilowatt, and QL will be S into sine phi, it will be 12 root 3 into 0.6, so it will be 12.47.
Option D, sir.
Option
D, D.
yes, 12.47. Very good. So in this problem, nothing is there. So we can make the power triangle. Here in this problem, it is asked about the unity power factor. That means total reactive power at the input is 0. So whatever the QL is, it is just opposite to that capacitive reactive power. So QC is equal to QL. So earlier this angle, whatever this angle power, there nothing relation with this, but QC value is minus of QL. So it is minus of 12.47 kVAr. So option D is correct. Now next problem is that at an industrial substation, with a 4 megawatt load, a capacitor of 2 MVAR is installed to maintain the load power factor at 0.97 lagging. If the capacitor goes out of service, the load power factor becomes. So here we are given with this power factor after compensation. So phi 2 is given, cos inverse 0.97, power factor angle is 14.07. So let us make the power factor triangle. So this is PL. PL is given as 4 megawatt, and we are given with QL also. QL is given with, QL is not given. So we are given with power factor. This is initial power factor, and then after power factor correction, this will become phi 2. So phi 2 is given 14.07. This is QC. So this will be QL minus QC. So we have to find this phi 1. Phi 1 is what? So we have to find this phi 1. So let us first find this QL, because QC is also given. QC value is given as 2 MVAR. So we can use this phi 2 value. So we can write tan phi 2 as QL minus QC divided by PL. So that will give you tan phi 2. Phi 2 is 14.07. QL is, you have to find, and QC is 2, and PL is 4. So it will give 1 is equal to QL minus 2. So this will give QL is equal to 3 MVAR. Therefore, phi 1 we can write tan
Sir,
inverse.
option C.
Option
C, C.
is correct. Very good. Tan inverse QL. Now I think any question asked from this power factor correction, reactive power compensation, no question will. I think no one will left from this part. And this is very scoring one also. They cannot
Yes, yes, sir.
manipulate much in this part. Sometimes just I think you need to be careful with sign convention, but that's it. Cos phi 1 will be 0.8 lagging. So this is from GATE 2005. It is up 2 marks. So now let us see the next problem. So the next problem is that for the system shown below, SD1 and SD2 are complex power demands at bus 1 and bus 2 respectively. If V2 is equal to 1 per unit, the VAR rating of the capacitor connected at bus 2 is. So since this is lossless transmission line, so we can apply this expression for power. So we know that P is equal to V1 V2 divided by X sine delta. So since this SD2 is 1 per unit, so this power is, from here we can say that active power flow through the line is 1. So we can write this one as 1 and V1 is 1 given, and we are given with V2 also. V2 is given as 1 per unit and X is given as 0.5 sine delta. From here you will get delta value. So delta is coming as 30 degree. So V2 you can write as 1 at the angle of minus 30 degree per unit. Now we can write the reactive power at bus 2. Reactive power at bus 2 using this reactive power flow equation. So we have seen that Q2 will be V1 V2. Wherever this reactive power is calculating, their cost term will not come. Just remember like this. So it is at bus 2. So at bus 2 side, we have not to write cost term. So Q2 will be 1 divided by 0.5, cos 30 will be root 3 divided by 2 minus 1 divided by 0.5. So finally this will give Q2 as root 3 minus 2. So it will give you as minus 0.268 per unit. So this the net reactive power at this input side at this bus 2 should be 0. So Q2 plus QC will be 0. So QC will come as 0.268 per unit. So option B is correct. And this is asked in GATE 2012. So and these next problems I have solved previously. So just go through it. And this question 8 is asked in GATE 117 and it is also of 2 marks. And subsequently we have solved also one problem from GATE 2014. These are all basic problems. Okay, all right. So any doubt till here? Viraya?
No,
No,
sir.
sir.
No, sir.
Okay. Thank you all for attending the session, and we will meet on the next Saturday.
Thank you, sir.
Thank you, sir.
Uh,
Thank you, sir.
Thank you, everyone.